Introduction. Today, our physics teacher is going to perform an experiment in the physics lab. She starts the experiment in front of the students. She took a cardboard having a hole at the center. She made an electronic circuit and passed the wire from that hole. Then, she sprinkles the iron dust on the cardboard uniformly. After set up the arrangement, she switches on the circuit. When she switches on, some movement is shown in the iron dust particles and they start arranging in concentric circles pattern. She performed this experiment to show you the magnetic effect of current. You saw the iron dust particles arranged into the concentric circle pattern due to the magnetic field generated by the electric current. Students, today we'll study more about the moving charges and magnetism. Lorentz force. A charge Q moving with a velocity v in a magnetic field B experiences a force generally known as the magnetic Lorentz force. It is given by F is equal to Q into cross product of V and B. In magnitude, F is equal to QVB sin theta. The magnetic force on a charged particle moving in a magnetic field has its maximum value when the particle moves perpendicular to the magnetic field. F max is equal to QVB. Minimum value when the particle moves in the direction of the magnetic field or opposite the field. F minimum is equal to 0. Magnetic force on a current-carrying conductor. The moving charge carriers constituting a current in a conductor experience magnetic force when the conductor is placed in a magnetic field. We consider a segment of a conductor of uniform cross-sectional area A carrying a current I in a uniform magnetic field B. We consider a current element I dl of the conductor. The number of free electrons in the element dl of the conductor is NaDl, where N is the number density of free electrons in the conductor. The magnetic force experienced by the current element IdL is given by minus ENaDl into cross product of V and B, which is equal to I into cross product of dl and B, where I is the current in the conductor. The resultant force F on the conductor is the vector sum of the contributions of all the elements constituting the conductor. Now we get the result F is equal to I into cross product of L and B. The magnitude of magnetic force on the straight conductor is given by F is equal to BIL sin theta. Example. Let's take an example of magnetic force on a current-carrying conductor. A horizontal wire 0.1 meters long carries a current of 6 ampere. What magnitude and direction of magnetic field can support the weight of this wire, where mass is 3 into 10 raised to the power minus 3 kilogram? Let's see the solution. Here, the given values are L is equal to 0.1 meters, I is equal to 6 amperes, M is equal to 3 into 10 raised to the power minus 3 kilogram. Force due to magnetic field on current-carrying wire when the field is normal to the straight conductor is equal to BIL. Weight of wire is given by mg. On comparing these two equations we get BIL is equal to mg, which can be written as B is equal to mg divided by IL. By putting the values and calculating, we get the value of B is equal to 0.49 Tesla. Hence, magnetic field of 0.49 Tesla can support the weight of the wire. Torque on a rectangular current loop. We consider a current-carrying rectangular loop PQRS of sides A and B placed in an external uniform magnetic field B. The normal to the plane of the loop makes an angle theta with B. When a current I flows through the loop, each straight segment experiences a force. The forces F1 and F3 are equal in magnitude, opposite in direction and collinear, so the net force and torque due to these forces are zero. The forces F2 and F4 are also equal in magnitude and opposite in direction, so they produce no net force. However, since the two forces are not collinear, they exert a torque on the loop, with magnitude equal to product of force and lever arm, which is equal to IAB sin theta, where A is the area of loop. The above equation can be written as tau is equal to mb sin theta, where m is the magnitude of magnetic dipole moment. Tau is equal to the cross product of m and b. Moving coil galvanometer. The galvanometer is a device used in the construction of both ammeter and voltmeter. It works on the principle that a current-carrying coil suspended in a uniform magnetic field experiences a torque which balances the restoring torque produced by the twisting of the suspension spring. The galvanometer consists of a coil of fine wire of many turns wound on a cylindrical soft iron core hung from a spring and carrying the current I to be measured. The pole pieces are cylindrical in shape so that the coil rotates in a field that is everywhere radial. This radial force ensures that the deflecting torque is directly proportional to the current and is always constant. Parameters of moving coil galvanometer. The steady deflection for a galvanometer is given by NBA upon K multiplied by I, where N is number of turns in the coil, A is the area of coil, and K is the torsional constant of the spring. The current sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit current flows through it. Current sensitivity is equal to phi upon I, which is equal to NBA upon K. The voltage sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit voltage is applied across it. Voltage sensitivity is equal to phi upon V, which is equal to NBAI upon KV. Conversion of galvanometer into ammeter. To measure the current in a circuit, an ammeter must be inserted in series in the circuit so that the current to be measured passes through it. The range of the galvanometer can be extended, and at the same time, the equivalent resistance can be reduced by connecting a low resistor S in parallel with the galvanometer. The resistor S is called the shunt resistor. The galvanometer and parallel resistor combination is called an ammeter. V is equal to product of Ig and G, or V is equal to product of Is and S. On equating both above equations, we get the value of S is equal to Ig upon Is into G. We know that I is equal to Ig plus Is. Hence, the value of S is equal to Ig upon I minus Ig into G. With this value of S, the ammeter is able to measure a large current up to I, and it has a low resistance. Conversion of galvanometer into voltmeter. To measure potential difference across a given section of a circuit, the voltmeter must be connected in parallel with that section of the circuit. The range can be extended, and at the same time, the equivalent resistance can be increased by connecting a resistance in series with the galvanometer. The galvanometer and series resistor combination is called a voltmeter. Applying Ohm's law to the circuit, we get V upon Rs plus G within parentheses is equal to Ig. It can be written as Rs is equal to V upon Ig minus G. Rs must be put in series with the galvanometer in order that it may be used as a voltmeter. The voltmeter has a high resistance Rs plus G within parentheses. Did you know? A solenoid switch is used as a control device. It utilizes electromagnetic energy so as to convert the input electrical energy to mechanical energy. Modern uses for the galvanometer mechanism are in positioning and control systems. Solenoid is used as an interlock device for integration into automatic gearbox drive selectors, petrol cap locking, vibration engine mountings, and security systems. Summary. Let us summarize what we have learned. Ampere's circuit law relates the integrated magnetic field around a closed loop to the electric current passing through the loop. A solenoid is a current-carrying wire wound around the surface of a right circular cylinder. A toroid is a current-carrying wire wound around a donut-shaped core. When the currents are in the same direction in the two conducting wires, the forces between the wires are attractive. 1 ampere is that current which, if passed in each of the two parallel conductors of infinite length and 1 meter apart in vacuum, cause each conductor to experience a force of 2 into 10 raised to the power minus 7 Newton per meter of length of conductor. Right-hand thumb rule states that if the current is directed along the 4 curved fingers of the right hand, then the extended thumb points in the direction of the magnetic dipole moment. Moving coil galvanometer works on the principle that a current-carrying coil suspended in a uniform magnetic field experiences a torque which balances the restoring torque produced by the twisting of the suspension spring. The current sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit current flows through it. The galvanometer and series resistor combination is called a voltmeter.